Well, hello and welcome again to our journey into complex analysis and looking at section 12, which is one of the applications of all our residue theory to improper real integrals. So we're going to look at some applications of this to these improper real integrals. I'm going to look at various different types of this. So we recall firstly that when we write an expression like this, integral 0 to infinity, what we mean is we chop this off at some point r, and we take a limit as r goes to infinity. And if we've got a double-ended integral, then by this we mean that we chop it off at r, we go from 0 to r and from minus r to 0, and we take limits independently as r goes to infinity. That is, if this limit exists, so if each of these limits exists, and then we say that this exists and is equal to the first integral. Now the converse of this is false, of course, but hence we're going to define what we can call the Cauchy principal value of these integrals simply to be the principal value of this integral. We define to be the limit. We go from minus r to plus r at the same speed, so not independently, we just let r go to infinity, and if this exists we call this the Cauchy principal value. So in most of the examples that follows we will find the Cauchy principal value of the improper integral. However, in each case, unless otherwise specified, these will in fact equal the improper integral itself. That is, we could have split this up into two integrals and looked at each of these separately and checking whether the limit exists separately. So you should check by the comparison test that each of the integrals we're looking at does in fact converge in the usual sense. So a fairly simple one to begin with. This one you can do by elementary methods. You can factorise the quartic in the bottom as a product of two quadratics with some root 2's in them. You can then grind through some partial fractions, and if you complete the squares you can get some inverse tans, I think, and you can work out this integral directly if you wish to, but we're going to do it using complex analysis. So here is the worked solution to this one. You'll see it's a very nice example of the application of residues. So we're starting off with this real integral, no complex numbers, just a perfectly good real integral. And I'm going to immediately complexify it. I'm going to look at a corresponding, it doesn't equal it at the moment, but I'm going to look at a corresponding complex integral. And all I do is I replace the x with a z everywhere. And if we're going to integrate, it's going to be a contour integral. We're going to integrate around a contour gamma. Now this gamma is going to look like this. We go from minus r to r along the real axis, and then we go into the upper half plane via a semicircle of radius r. So this gamma r is a semicircle. This is a semicircle, radius r. And for the sake of argument, I'm going to take r bigger than 1, just to, I haven't got to worry about it, and we're going to think of taking limits. Now you can see as r goes to infinity, the integral along the real axis is going to go back and approach the one we started with. So what we have to worry about is what is the contribution, once we've evaluated things, what is the contribution to this integral of this integral around gamma r. And we'll come back to that in a moment. So just for notation's sake, we let f of z be equal to z squared on z to the 4th plus 1. And to use our residue theory, we need to know what the singularities are inside this big contour capital gamma. And the singularities are going to occur when the denominator here is 0. And that's an easy one to solve. We get z as e to the I pi on 4 and 3 pi I on 4. Now these are the ones in gamma. We're only interested in singularities inside the contour. So of course there are two more singularities down here, but we don't care about those. The ones inside the singularity are at e to the I pi on 4, which are roughly there, and e to the 3 pi I on 4. And to save writing those, I'm just going to call them alpha and beta. Now if you think about it, this z to the fourth plus 1 in the complex plane falls to pieces into a product of 4 linear factors, and the z minus each of these will be 2 of the linear factors, so these are going to be simple poles. And we can check that and get the residue by simply using our usual limit here. So the residue of f at z is alpha, you multiply the function by z minus alpha and take a limit as z goes to alpha. Now you could factorise this into z minus alpha bar, z minus beta bar, and then cancel it out, and then plug in the thing and simplify it, but that's very tedious. It's much better to let L'Hopital do all the work for you. This is a rather sweet application of L'Hopital. Notice that when you take this limit, when you're putting z as alpha, that is 0, that is 0, that is not 0. So evaluate this first and write this as alpha squared. And then you can apply L'Hopital to what's left. So you differentiate that, you get 1, differentiate that, you get 4z cubed, put in z as alpha, you get 4 alpha cubed, and you get 1 over 4 alpha. Now of course exactly the same calculation happens for beta, so the residue at beta is also going to be 1 over 4 beta. Finally then I can work out my j by taking 2 pi I times the sum of the residues. Now so I take a quarter out. Now 1 over alpha is e to the minus I pi on 4, and 1 over beta is e to the minus 3 pi I on 4. And you can expand these out, and you'll see that and simplify, and you'll see that when you write this out as cos pi on 4 minus I sine pi on 4 and so on, you'll see when you simplify you just end up with pi on root 2. The i's cancel out. Okay, so that's rather nice. And then we now need to, we've worked out this j integral. That's the one. This is the one here, this complex integral. And this was the integral from minus r to r, followed by this integral around gamma r. Well, we'd like to know what contribution this integral around small gamma r is making to this integral. And so now we're going to use our ML estimation lemma that we've seen before. So we're going to look at the modulus of the integral of f of z around little gamma r. And this will be less than, now the length of the contour is pi r, and the maximum modulus of the function on gamma, if I'm on gamma r, then mod z is just equal to r, so that's r squared. And then I've just popped it in here using the second triangle inequality. Mod z to the fourth plus 1 is bigger than r to the fourth minus 1 in modulus. Remember, r is bigger than 1, so I can forget about the absolute value sign. And plugging that back in here, we get the rest of the approximation here. Now we get an r cubed term on the top, an r squared term on the bottom, so the bottom dominates. And that means this is going to go to 0 as r goes to infinity. Now just enjoy that, because that's very lovely. We added in, we were really interested in the integral along the real axis. We added in this extra bit up here on this semicircle, and then as r goes off to infinity, the contribution to our integral up from the top part goes to 0. We introduced it, and it kindly exits as r goes to infinity. So this integral j, whose value we know, is the integral along the real axis from minus r to r plus this integral along gamma r. And as r goes to infinity, this goes to 0, because of course if the magnitude of the integral goes to 0, well, the integral goes to 0. And this bit turns back into our I integral that we started with. And that means j equals I, and so there's the value of our integral. It's pi on root 2, which, as I said, you could have gotten by elementary means in this case. Second example's a little bit more esoteric, but shows you the power of complex analysis here. We're doing the integral from minus infinity to infinity of sine 3x plus 2 cos 3x over this quadratic dx. And this one I don't know how I would do by any sort of elementary method. I don't know how I would do this if I didn't have complex analysis. So here's the worked solution for this. So there's the integral we're working with. Now, by the way, this integral converges absolutely by the comparison test. So it's got a, because the top is bounded by, say, 3, and so this is going to be just a constant over a quadratic, and this is going to be so this will in fact converge, and its Cauchy principal value will be equal to the value of the improper integral. Now we want to get some complex, when you get sines and coses in the story here, you want to get some complex numbers into here, and when you see sine and cos, you're thinking of real and imaginary parts of things. So this is the real part of, well, this term here, this is the real part of 2e to the 3ix, and if I take e to the 3ix and multiply by minus I, then the real part of that will be sine 3x. So that's just a little trick there to rewrite the top in terms of exponentials. And you have to do that in order to get the bounding argument to work a bit later. So that just stays the same. And then I can factor out an e to the 3ix here, and so I just get the real part of 2 minus I times this integral. So this is the integral we're interested in, and so once again we're going to consider j, take this integral, replace x with z, and then take a contour integral around capital gamma. It's the same contour as before. You go along here and then back around here. So giving this function in here a name, call that f of z, then it's got singularities when the denominator is 0, and it turns out to have complex roots, and the only root that's inside gamma is minus 2 plus I. So minus 2 plus I is there. The other root is minus 2 minus I, and that would be down here, which is outside the contour. So in the contour, f has one singularity at minus 2 plus I, which again I'm going to call alpha. And again I claim alpha is a simple pole. And we can check that and get the residue as well, all in one calculation. So we multiply the function by z minus alpha. Again, you could factor the bottom and do cancellation, just much better to just use L'Hopital's rule. Now again, as z goes to alpha, this is going to 0, this is going to 0, this is not going to 0, this is just e to the 3i alpha. And then I can use L'Hopital in what's left. So that differentiates to 1. This goes to 2z plus 4, and I replace z with alpha. Now, if you take your alpha from up here and you double it and add 4, you just get 2i. And I'm replacing the alpha with minus 2 plus I, which gives me this expression here. So j then is 2 pi I times the sum of the residues. Well, there's only one. So the 2 pi goes out, sorry, the 2i goes out with the 2 pi I. I get a pi left. I've got an e to the minus 3 from here. And I did get that correct, didn't we? That's, it's 3i times that. So that's minus 6i. And 3i times that's minus 3, yep. So we have this expression here, pi e to the minus 3, and I get e to the minus 6i, which is cos 6 minus I sine 6. So there's the value of j of the integral, the complex contour integral. We'll come back to that in a moment. Now we're going to just do the bounding argument, so I want to see what's happening along gamma r, and again I need to do a little bit of side calculation here. If we take z on gamma r, then the numerator here, e to the 3iz, this is equal to the modulus of 3ix minus 3y when I put z as x plus iy in. The modulus of this is the same as modulus, is just e to the minus 3y, and that's less than 1 because y is positive on gamma. So when I use my ML estimation lemma, then the length of the contour is pi r. The maximum modulus of e to the 3iz is 1. And then I simply use the triangle inequality, the second one, a couple of times, and I see that the 1 over z squared plus 4z plus 5, modulus of that is less than 1 over r squared minus 4r minus 5. Now once again, we've got an r squared on the bottom, r on the top, the bottom wins, and so this goes to 0 again as r goes to infinity. So again, the contribution to our j integral along gamma r, small gamma r, is 0. And again, we can split this up into the integral along gamma r plus the integral along the real axis. So this is now f of x dx. And as r goes to infinity, this goes to 0. And we're just left with this thing. And that's equal to j, and we know the value of j from before. Now, I was the real part of 2 minus I times this integral. That's what we had back up here. Was real part of 2 minus I times this integral. So real 2 minus I times this expression that we got from before. So this is over part e cubed. And again, if you just pull out the real part, multiply this out and pull out the real part, we end up with pi over e cubed, 2 cos 6 minus sine 6. And there's the value of the improper integral. And as we see, that's a rather, it's a problem which I'm not sure one could do easily, if at all, by using elementary methods. Now, what made all this work, of course, was the fact that this bounding argument that we did here, that the contribution of gamma r went to 0. Now, in some problems, the bounding argument just used barely like this doesn't always work. And especially in problems where we're interested in the Cauchy principal value, which may or may not equal the actual value of the improper integral. So I'm going to need some slightly more sophisticated machinery, which we'll see in the next recording, where we're going to have a look at Jordan's lemma.